Hey, it's Mr. Shrum. Yeah, we're good. Okay. And I am here with another tutorial for physical science. And we're going to go over graphs and relationships and see if I can help you out in any way through this tutorial. Sorry, I said tutorial weirdly. But our objective here, we're going to plot graphs and recognize the relationship and data. Fun stuff. And it's useful. This is good if you're a very visual person. Yeah. But here's the intro. I'm sure you've seen a graph, certainly, in your life. Business people use them. Scientists use them. I'm sure your parents have seen graphs and use them to some degree in some of their jobs. But scatter plots, line graphs, the Cartesian coordinate system, and that's just a fancy way to say the XY axis chart. You've seen it. We all know it. But graphs are good because you can see data. If you're given a bunch of numbers and someone just starts listing off numbers like 200, 212, 300, 320, there's not a lot of meaning behind that, and it's hard for you to like visualize that in your head. But if someone makes a graph and draws you a picture, it's easier for you to understand the numbers. It gives some type of meaning to the numbers and data. So it helps you tell a story about what's happening. Think of graphs as like scientific storytelling, a little more artistic way of showing what's happening in science. But here we go. Here we are on the Cartesian plane, the Cartesian graph. But we have your x-axis down here, good old x-axis. And then we have the y-axis, right? Why? Why? I don't know why. But we're given two words, two fancy sounding words, interpolation and extrapolation. So we got the polations, in common. So they must be related to some degree, right? So let's read a bit about what they're saying here. Graphs provide a visual representation. So if something's super complex, a graph can make it a little easier to understand. Interpolation, extrapolation. Interpolation, you can estimate a value that lies between two known values. So say you already know this point and you already know this point, and you want to know something in between. You're going to have to interpolate because it's in between two things you already know. If you want to extrapolate, you have to go above and beyond, extra. So if you know these points, but you don't know any points past this point, think of that as extra, additional. So you're going to have to extrapolate. You're going to have to use what you know to find out what you don't know. That's a lot of science. You take things that you already know, to find out things that you don't know. And this is a very you'll get used to this equation, y minus y naught. We refer to that little zero as naught, at least most scientists do. So if you want to sound like you know what you're doing, say y naught. So y minus y naught equals bracket y1. So you just say the number and then just say y naught. y1 minus y naught over x1 minus x naught, bracket, times, parentheses, x minus x naught. Okay, so you see here, this point is x naught, y naught. This point is x1, y1. And the point you want to know is just xy. So the numbers with the littler number, the little brother number, is stuff you already know. Okay, and then y and x is the thing you don't know, and you're gonna solve for those. Okay. Let's see. Yeah, we're just gonna jump into an example. That's the best thing to do with math. Just throw you in and see if you can catch up. You know what I mean? I think you know what I mean. Okay. So to stretch a spring, we need to apply force. Force. And here we go, force. And those are in newtons. And then we're measuring elongation. Elongation, fancy science word for how long the string is pulled. And that's measured in centimeters. And if you remember from the prefix lesson last time, centi means 1/100th of a meter. Remember that. So look at this graph. We have force, the thing you are changing on purpose on the x-axis. Y-axis, elongation, the thing we're looking for. Like if we're changing the force, we're looking for how much change there is in elongation, right? And it looks like the relationship between force and elongation, pretty straightforward. As force increases, elongation increases. But by how much? We'll find out. Actually, it kind of tells you already. So the relationship is linear. And knowing this, we can interpolate, and extrapolate. So if we know the point between F2 and F3, you can solve for the elongation if F equals 2.5. So 2.5 is between 2 and 3. If the force is 2.5, you just plug in the numbers you already know. So we're looking for x. We subtract x naught. And then, yeah, so if you go back to the formula here, sorry, to give you another, so remember this is the equation before we put numbers in. And then once you put the numbers in, you are left with x equals 1.25 centimeters. Okay. That makes sense. Here it's a little different because I hope you don't get confused by this, but you see how the x-axis is x's and y-axis is y. However, this is using f for the x's, and then it's using x, which is the symbol for displacement or elongation for the where the y should go. But don't let that fool you. If you just plug in the numbers, f for here and then x for here. Plug in. We're given 1.25 centimeters. And you can always check here, right? So if you know 2, the force is 2 and you get 1 elongation, 1 centimeter of elongation, and if F is 3, you get 1.5, your answer should be somewhere between 1 and 1.5 elongation. And it was 1.25 for elongation. So with these types of linear relationships, it's easier to use your eyes, right? However, things can get a little trickier. If you look at like a certain point, it's harder to guess, a little harder. So that's the time to stick to the equation, all right? So think of this as being the x-axis numbers and the y-axis numbers. So once again, distance is at y, the y-axis. However, they're using the x's to describe the change in distance. But the x-axis are t's and the y-axis are shown with x's in this example. But it's the same formula as this, okay? Even though they're using different letters, it's the same thing. Pay attention to what's used in the x-axis and the y-axis. And then all you have to do is plug in what you're trying to figure out. So at 1.5 seconds, you can see the car has moved about 2.25 meters. Then you can use the formula to estimate this value using the known point at t equals 1 second and t equals 2 seconds. So you plug in 1 for the distance here. And then you have 4 minus 1, which is the difference between this y-axis, right? 4, 1, over the x-axis numbers, 2, 1, okay, times the difference in time for t and t naught. So t in this case is the one we're looking for, 1.5, the point we need, and then 1 is the known point. So we have the x that we want to know, the x-axis we want to know for that one. And you're given, after 1.5 seconds, the distance covered is 2.5 meters, which is fairly close to the value on the graph. The slight variation is due to the linear approximation. So because this is not a directly linear relationship, this equation is not as accurate, okay? That's where we estimated, but if you look at the actual graph, it's a little off. So you can estimate, you can get pretty close, but you can't get spot on. That's why we say estimation. So this was an example of interpolation, because you were looking for the point between 2 points you already know. And this is extrapolation. Okay, you're looking beyond. according to the graph, at 2.5 seconds, the car has covered about 6.25 meters. If we didn't have the graph, if you didn't have the graph, you could use the math below to figure it out. And like we said, you plug in x naught, y1 minus y naught, t1 minus t naught, times 2.5 minus 1. Okay. That looks like a typo. So ignore that minus sign. This should be a multiplication. So we have x minus our known point on the y-axis for this one, 1, equals x1, which is the difference between the y-axis numbers, 4 minus 1, 4 minus 1, over the difference in x-axis, 2, 1, okay, times the t we're looking for minus t naught, which is this point. So we're looking for 2.5, but it's beyond the points we already know. So we're using this x-axis number to figure it out. And so with our extrapolated value, it comes out to about 5.5. Okay. Once again, because this is not a linear relationship, this only gets close, but it's not quite accurate because the relationship itself is not linear, but we're using linear approximation. You're getting close, but not quite the right answer. Because you're acting like these points are on a line like this and not how it's actually shown, okay? So this will get you close. A lot of times in science, at least practical science, you want close. So if something will take a lot of time to get super accurate, a lot of time and money, approximating may be the right choice to go. But remember these words: interpolation, you're looking between points you already know. Extrapolation, you're looking for points beyond what you already know, okay? Inner, extra, outer, extra, past the beyond point. I hope that makes sense and helps you understand. So, using this graph and the table, interpolate to find the potential energy, U, at a height, h, of 2.5 meters, and extrapolate. So what does extrapolate mean? We're looking beyond what we already know, the points we already have, to find the potential energy at a height of 4.5. So h is our x-axis, height. Potential energy, U, is our y-axis. Here we're giving the graph points and then the actual graph itself. So which of these are correct? At 2.5 meters, the potential energy would be, well, let's look. So here's 2, a height of 2, and between a height of 3. At a height of 2.5, what does it look like on the y-axis? If each of these points is 10, so we have 20, 30, 40, 50. it would be 50 joules. Using this equation, and then at 4.5, what do you guys think? Looks like 90 joules. But if we did not have this graph and we were just given this number, you would use this equation, right? So use the U is the y-axis numbers, how we describe potential energy. That's the scientific letter we use, and then H, height. That's easy to remember. A lot of these different letters come from Greek and words that are not English. So we're like, well, that doesn't really make sense to me. But it's somewhat arbitrary. Someone did it in the past, and then we just kind of went along with it. And that's why potential energy uses the letter U for now. And now we're talking about common graphs. So this is the Cartesian graph, right? XY axis. It's named after René Descartes. A French mathematician in the 17th century. Very fairly intelligent person, I'd assume. Sure, I never met the guy, but this Cartesian graph has two axes. Horizontal is x, vertical is y. 0, 0, that's where they intersect, and that's our starting point for most graphs. The slope of the graph is the ratio of change in the y coordinates over the change in x coordinates. And if we know the slope and we're given a certain point, you can find your way along the line. If the the relationship is linear like that. If it's a different type of relationship, things get a little more complicated. So linear graph, like we said, super easy. It's just a straight line because as something increases, another thing increases at the same rate. So y equals the slope times x. Wow, this feels a lot like math. Is this math class? This is supposed to be science, right? Well, we use a lot of math in science. So it's important to kind of know what you're doing so you don't look like an amateur. We don't want to be amateurs in here, right? Only pros allowed in physical science. And you're about to be a pro. If you're not already, you're about to be a pro. But yeah, it just gives you another example. But yeah, it says it can be confusing when you're using variables that are not x and y. So I just pretend they're x and y and use those as the variables in my head. It's just easier for me to think of the axis as x and y instead of t and then d or x and then yeah. So if that helps you, then do that. Do like x equals time in seconds and then y equals distance in meters, and then just write out the x's and the y's and just keep them the same. Now, if you have an inverse graph where the slope is a fraction, where k is a non-zero constant, when x increases, Yeah, when x increases, the y decreases. So, sorry, it's not linear. I misspoke again, sorry. Linear, straight line. Inverse, you're given a constant, k, divided by x. So as the x goes up, the y is decreasing. It's the opposite, the inverse, right? One goes up, the other goes down. Y equals infinity. It just keeps on going up when x equals or approaches 0. It's just way up here. But a lot of the times we're not interested in that. We're interested in this stuff over here. And then as x gets incredibly large and goes towards infinity, y gets super, super small. But we're usually more invested, and we want to know what happens in these points. We don't really care about infinity right now or 0. Excuse me, sorry. But this is a good visualization between the difference of a linear plot and an inverse. So linear, one variable increases, the other increases. If it decreases, the other variable decreases too. And then inverse is opposites happen. One increases, the other decreases. If one decreases, the other increases. Okay. And this gives you an example. P. Yeah, so pressure and volume, they will be represented with P and V. Of an ideal gas at a particular temperature is always equal to a constant value. And so in a mathy way, we can say P times V equals a constant K, or P is proportional to 1 over V. And this simple symbol just means proportional to. So as pressure increases, the volume decreases, and the other way around. So that means the relationship is inverse. As pressure increases, volume decreases. As pressure decreases, volume increases. Okay? Quadratic parabola. This is another type of graph that's a little more complex than linear plots. Y equals ax squared plus bx plus c. A, b, c's are constant. If b and c are 0, y equals a times x squared, and the point is at 0, 0. So this thing would move, this point would be here if b and c were not in the equation. And it can either open up or down based on the value of a. If it's positive, it opens up. If it's negative, it would curve downward. And you can open up the interactive graph and see what happens. I think that's a good way to learn about this, is just to mess around with equations. But we have a lesson activity. And you're asked questions about the graphs and how to describe what's happening. And what variables go where, okay? How would you describe the car's velocity? Once you click on the link, discuss both its speed and direction. Mention any change to speed or direction you observe. This is just you describing stuff. Predict the shape of a graph that shows distance versus time. Now that time is the independent variable, note that, so time is going to be on the x-axis, the horizontal axis. This says check your graph prediction. So you're guessing what the graph looks like based on what you know, the relationship between the variables. And then how do you think it compared to your prediction? And then you're asked about velocity versus time, velocity in the x direction versus time. Then it says to compare your prediction in the graph again. Use the data from the table to calculate the average velocity for the car to one decimal place. So remember, the velocity is the change in distance divided by the change in time. The change in displacement divided by change in time. So it asks you to look at the video, play the video. Based on what you're seeing, describe the car's displacement, distance, and direction from the starting point over time. It asks you to run the video frame by frame and describe the velocity, speed, and direction again. And now you want to predict the shape of the displacement versus time and velocity versus time. And think about why you think it would have a certain shape based on what you already know about velocity, the displacement and velocity. And then ask you to test your predictions by changing the displays to graphs. And ask you, were you right? Were you close? Were you surprised by anything? And then ask you what type of graph you see and what is the mathematical relationship. Can you come up with an equation? At the head? Oh, excuse me. Based on the velocity graph, can you describe the acceleration over time? And if you know acceleration is the change in velocity, is it positive or negative? Is it speeding up? What's happening with it? And then ask you to change your prediction or to check your prediction by changing the graph to an acceleration versus time graph. And it tells you how to do that. And then, did your description match the graph at all? And this would self-evaluation. And this is good if you're like, oh, I understood it. My predictions match the graphs, or oh, I mine didn't. So I should probably look at these again and make sure I understand the relationship between the variables. Okay. So this is a good visualization. inverse when one increases, the other decreases. Quadratic. So quadratic, always remember there's some type of parabola, something curvy is going on. While linear, it's more straightforward. There's a line, a straight line. As one increases, the other increases. As one decreases, the other decreases. And then we're given a summary. Graphs help scientists understand complex data. They can tell a story more easily and help people understand what's going on. This is the equation for a linear graph, a straight line, y equals slope times x plus b. An inverse graph is equal to k, constant, over x plus b. A quadratic graph, this parabola looking thing. So we have linear, inverse, and then parabola. 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 It's a fun word. Y equals ax squared plus bx plus c. Okay. So this one has the most going on. Anytime you see an x squared, think of quadratic. Or just an x squared and an x, quadratic. Something over x, inverse, just an x, linear. All right. And there we go. That has been that tutorial, graph and relationships. I hope I helped you understand a little bit more about this lesson. And the more we use graphs and look at relationships, the better you're gonna know, the better you're gonna understand what's happening, right? So play around with those simulations. Simulations are really good because you can do your own changes and see what changes the graph and how you can turn a quadratic equation into different looking graphs. You can turn it upside down. You can move the parabola. And that's all with the mathematical equations. All right. Okay. I will see you guys later. Bye-bye.